So where the last video discussed a formula, and in particular we discussed sodium carbonate, and it allowed us to look at that formula and recognize that we could then say we had two atoms of sodium in one, sorry, there's not enough space there, one molecule of sodium carbonate, or we could go through and have said 2 moles of atoms of sodium were equal to 1 mole of molecules of sodium carbonate. So that was useful because we had those now ability to convert between substances using chemical formulas. Well, a chemical formula is very similar into a chemical reaction or to chemical equation, because the chemical equation now allows us to convert one substance to another through a effectively legitimate process. If we go through and look at our formula, we're kind of arbitrarily making the connection of sodium in sodium carbonate. Might be nice if I put in that C. That isn't how it's made. How to make it would require an actual chemical equation to understand that. So what the formula gives us is this ability to convert within the formula, but it's kind of an arbitrary system because we can't actually make those things happen. The chemical equation actually allows us to make those things happen. Okay? And that's why chemical equations become useful. If we were to go through and try and provide simple instructions, so again, what we're going to do is step back from the chemistry and look at a larger thing. So if we were to provide instructions on how to build a bicycle, assuming we just had wheels and a frame, well, we could go through and say that we need those 2 wheels, and we put those 2 wheels together, okay, and this is our putting together process, we get our bicycle, and so we've assembled it. We could also simplify this because we have that repetition of wheels, and that takes up more space, so we could put a coefficient in front. 2 times wheels plus that frame gives us the bicycle. And so now we have a chemical equation to represent this process. So we could then use this chemical equation to come up with some answers. So if someone built 4 bikes, how many wheels and frames were used? Okay, you could probably come up with that calculation pretty straightforward and simply in your head. Okay, but as we've been talking about again and again and again, don't focus on, yes, I can answer this question. Focus on what was the process you used to answer that. And for those of you saying, well, I just multiplied by 4, that doesn't really work either because you're only answering this question. Okay, we again want to scaffold out to the process that we've been using. So in this question, we're asked 2 things. We're actually asked how many wheels and how many frames. So it's really 2 separate questions. So if I want to know how many wheels were used, I would have to use the given information. Okay, I'm given that I have 4 bikes, and I'm given this big equation that now shows all of those intricate pieces. So which piece of information do I want to use first? Okay, the analogies that we've been using in the past is that we probably would want to move to using the purple information first. I want to use those wheels from the purple information because those are the same unit, whereas bikes isn't the same unit as wheels. Because I'm pulling it from the purple information, I know that that is 2 wheels. Okay. Now, what do I want to relate those wheels to? I could relate them to frames. Am I spelling wheels right? Looks like it, allegedly. I could relate them to frames, but that's not useful because I'm not given frames. So instead, I'm going to relate those wheels to bikes. What is that conversion? Well, there's 1 bike. How do I know that? I looked at the chemical equation, and there's an implied coefficient of 1 in front of that. Okay. In my conversion process, that now introduced this concept of bikes that I don't want, so I would need to cancel that, which means I know bikes needs to show up in the numerator so that that unit can cancel. Am I given just bikes? Sure enough, I am 4 bikes. Okay, so the process is establishing where those units belong and how we multiply this out, and we would then say that we need 8 wheels. We would do the same thing for frames. So I'm going to say you should go through and actually write that down now. pause the video. You're not writing it down. Pause the freaking video. And ta-da, there's the answer. If I get a bit tense, sorry, I'm getting a bit stir crazy. My office at home is literally a 5x5 closet. So with that, we could go through and set up our work, and our answer comes out as 4 frames. So to build 4 bikes, I need 8 wheels and 4 frames. We might be, okay, that's simple. We understand that process. Okay, well, if you understand that, then you should be able to answer this question. So go through, set it up, pause the video again, see what you can come up with. Yeah, that means pause. That's the little click with your mouse, the 2 lines next to each other, or you can just click the picture. Just click in the middle and it'll pause the video. You didn't want to click? Try space. Just hit space, it'll pause the video. And your work should look like this. Ta-da! I'm amazing how fast I can write. So we get 3 bikes either way we look at it. Okay, so cool. Does your work look like this? If it doesn't, you should be continuing to go back, reverse the video, and try and establish what that process is again. Okay? Because again, that process becomes critical for when we make this more difficult. Okay, so let's try another one. Given just 2 wheels, how many bikes can be made? So again, set up your process and see what you come up with. You'll notice the video is still running, isn't it? That's because this is an interesting question. Okay? This is typically how a question would get phrased in chemistry, and it's actually poorly written. If you're only given 2 wheels, you can't make any bikes because you don't have a frame to which to attach those wheels. Guys, but unfortunately chemists do phrase questions like this. Okay? And really it's not chemists, it's chemistry instructors. What we're saying by this is given just 2 wheels, okay, and unlimited frames, how many bikes can be made? Man, that was awful. Let's try that again. And unlimited frames, how many bikes can be made? Okay. This is us being nice, because in the previous questions, you had to address both wheels and frames. By now saying unlimited frames, we don't have to calculate frames. We just have to worry about what the wheels are doing for us. Okay? So it's supposed to shorten the amount of work that we go through and do. We really should be a little bit more explicit and note that unlimited frames. So again, I'll give you that second, hit the space bar and go through and solve this. So again, space. And ta-da, we find out that we can make 1 bike. Again, showing all that work. Okay? We might be at a point now where people at home are being like, this is dumb. I don't need to show this work. Why would you make me show this work? Okay? My question to that would be, did you score what you wanted to score on the previous exam? If you did, then no, you don't need to show all this work. If you did not score what you wanted to score, and you feel like your score was abysmally low, then you need to show your work. Okay? To add a little bit more insult to injury, I added 10 points to everybody's grade. You didn't score high enough. Show your work. Okay? Given 3 wheels and 2 frames, how many bikes can be gone through and made? This one adds a little bit more complexity. Again, go ahead and hit that space for me and solve it out. And we go through and check our work. Our wheels cancel. And in one case, and of course I jammed it all up on itself, in one case we would go through and see that we could make 2 bikes, and in the other case we would see we could make 1.5 bikes. So that means in whopping total I could make 3.5 bikes. You're right, that doesn't make any sense. You can't do that. The only amount of bikes I would be able to make would be 1, because then I run out of parts. Okay? That's what happens in this relatively small scale. Okay, so we just kind of stop at that 1 bike because I can't have half a bike, and I certainly don't have enough to make a whole nother other bike. Okay, so we have to run both conversions to see which one produced the smallest amount, and then we predicted based off of that. Okay, I'm also going to take a moment here to say I do sort of apologize for the saltiness. I'm really trying to help you guys push with these formulas, and everybody is stressed. So I do apologize for that. Let's try and refocus and get back into dealing with our conversions. Okay, so now we've got the basic format behind our conversions. Let's add one more layer of difficulty to this, because why not? Given 40 grams of wheels and 15 pounds of frames, how many bikes can be made? If we immediately start launching into our system, we want bikes. We're probably going to have to do this twice, but we'll just kind of write through this and see what we got. Bikes, and then let's just say we're starting with wheels. 1 bike, 2 wheels. How many wheels am I given? And now we run into a problem. I'm not given a number of wheels. I'm given a measurement of wheels. Therein lies the problem with our conversion factor, or our chemical equation. A chemical equation does not relate mass, it relates numbers of things. Okay, it's a counting unit, if you will. Okay, which means as soon as we introduce this mass, a measurement, we're going to need a new conversion factor. I can't just write in my wheels. I'm going to have to relate the number of wheels to a mass of wheels. Okay? That new conversion factor is not found in this question, and therein lies the problem. We can't solve this question. We could go through and write out what we would need to do. We need that conversion factor so that we could then do 40 grams of wheels, and so that everything would cancel out nicely. But since I don't have that conversion factor in the middle, I'm kind of stuck and I can't solve this one. Okay, so we encounter the same kind of thing in chemistry. Our chemical equation gives us the power to convert between substances, but it does not allow us to convert between measurements. Okay, so we have to be very, very careful when we go through and use chemical equations. Okay, so let's go through and shift to a chemical equation and see what, and of course all of that stuff shows up. So we're going to do some quick erasures. If we went through and looked at the chemical equation, this is very similar to the bicycle. A molecule is now a single unit. This is effectively bikes, wheels, I know that's sloppy, and frames. Okay, so it's a single unit being produced in each of those things, or a single type. Okay, the exact numbers are kind of different and arbitrary for that individual system. So the power of this chemical equation is that it can be infinitely scaled upwards. So if, for instance, you were going to make cookies, you could make the cookies from the recipe off the back of the bag. But if you needed to make a whole lot of cookies, you could just scale those numbers up, okay, depending on how many cookies you wanted to make. You could just add more flour. You don't just randomly add those extra pieces. You add those ingredients according to the ratio that the recipe told you. Okay, that ratio is established in your recipe. What we have in a chemical equation is a recipe telling us the number of these pieces. Okay, so why do I want to scale up? Well, do you only want 24 cookies? Maybe you actually want 24 cookies because you're making cookies for the rest of the people on lockdown. So you're going to make little gift bags and drop off bags full of cookies to each of your neighbors. That'd be really cool and nice. Okay, if you were doing that, maybe I'd give you my address, but that's a whole nother thing. Okay, so because you probably won't give me cookies, you'll probably give me eggs, which is not what I need right now. So in a chemical equation or a chemical reaction, what are we scaling up by? So I could, instead of doing 2 molecules, scale this up. Well, let's make it 1 molecule. Instead of doing 1 molecule of O2, I could do 1,000 molecules. Why? Well, as we discussed in the past video, 1 molecule is too small to weigh out. That mass is incredibly tiny. If I scale it up to 1,000 molecules, I can improve the odds of me actually measuring it. But if I scale it up 1,000-fold, I need to scale up the other ones 1,000-fold as well. Okay? But that now holds, and those ratios are now maintained. Well, that's still such a small value, it won't allow me to scale up, or I still can't weigh it. So what I'll do is scale it up even more. And instead of going up by just 1,000 molecules, I'm going to go up by 6.022 times 10 to the 23rd molecules. Okay? And that does seem a bit silly of a number, but it's fair. And so for the NO, which is twice the amount of O2, I could just do 2 times 6.02 times 10 to the 23rd, and I would end up with 12.04 times 10 to the 23rd molecules of NO. Okay? And I could do the same thing with the NO2 to figure out how many molecules of NO2. This kind of scale up factor is similar to what we've already done. So let's backtrack here. I just said we multiplied that out and all of a sudden it magically worked. Well, let's apply it a little bit differently. If I want to know how many molecules of NO2 I'm going to have, I would need to convert from the molecules of O2 that I'm given into molecules of NO2. So molecules of O2 would need to be in the denominator. NO2 would need to be in the numerator. That conversion factor is 2 to 1. Where do I find that conversion factor? That's coming from the coefficients from my balanced chemical equation. That's where the math that we saw on this other side is coming from. Okay? Why do we want that work? We want that work because if we start doing multiple conversions, it's very easy to lose track. By writing down the work, we can see what's happening there. So when we go through and run that math, we would then end again with our 12.04 times 10 to the 23rd molecules. Okay, and we might encounter the same question of, well, why the heck would we scale it up so much? Well, we scale it up so much so that we can weigh it. Why did we scale it up by this particular amount? Well, 6.022 times 10 to the 23rd is a mole. So I could write this as 1 times moles. The 12.04 was 2 times 6.02 times 10 to the 23rd. What did we just say 6.02 times 10 to the 23rd was? A mole. Okay. Same deal on the other side. That 12.04 was really 2 times 6.022 times 10 to the 23rd. What did we say that was? We said that was defined as a mole. Okay. And why does this help us out? We don't have to deal with the powers of 10 anymore. We can simplify this down to saying I'm reacting 1 mole of O2 with 2 moles of NO and 2 moles of NO2 and producing 2 moles of NO2. The measurement unit, if you will, the counting unit from our chemical equation can be molecules. It can also be moles. Okay? Which one's more useful is going to depend on the context of what we're doing. For most of what we do in general chemistry, it's going to be moles, not molecules, because moles we can measure. We can scoop out a bunch of stuff onto the scale, onto a balance, and get a measurement, a mass measurement for that mole amount. We can't get a mass measurement for the molecules, so the molecule conversion factor from our chemical equation is effectively useless because it is just too small. Okay? The same kind of thing can apply back to our bicycles. If we looked at a bicycle, you might be like, well, 1 bike and 1 frame and all of that fun piece. Why do I need to scale this up? Well, I can almost guarantee it that if you go to a bike manufacturer in China and you tell them the formula for 1 bike and 1 frame and 2 wheels, they're going to be like, that's dumb. I don't care about making 1 bike. I need to make 50,000 bikes because that's how I'm going to exist as a company. It's that order of scale. Most people don't have to deal with that order of scale because you're not the high upper end administrator within that company manufacturing those things. Okay? As a chemist, you are now that high end administrator. And not only are you that high end administrator, you're effectively God level administration because you're not looking at 50,000 particles. You're looking at 10 to the 23rd particles. Okay? Astronomically different in complexity and size. And so that's why we invent these new units to simplify our life. Okay? So, with this, we can use that balanced chemical equation, and now we can answer questions of how do I convert moles of NO2, moles of N2 into moles of NO. Okay? Or how do I convert moles of O2 into moles of N2? Well, why would I do that? Well, if I have X moles of O2, how many of N2 do I need, okay, to run that reaction? So that single chemical equation, okay, so if we think back to what we've done before, we said, because this is the only one that I happen to remember, 454 grams was 1 pound. That expression, that equality, because that's effectively what we have here, is an equals, a chemical equation. The one expression that we did with our metric system, or even our English to metric, gave us 2 conversion factors. 454 grams is 1 pound, and 1 pound is 454 grams. So we get 2 expressions out of that for one memorization. Okay? So, and we could argue that we could just flip those back and forth, so it's relatively simple. A chemical equation becomes vastly more awesome in its potential, because if we look through those exact same types of relationships, what we end up with is now 9 relationships, or that's not 9, that would be 6 relationships, assuming there weren't duplicates, which I thought there were. We get a lot more relationships out of just this one chemical equation. Okay? If we think about the metric or measurement systems, those conversions, we got 2 conversion factors for one memorization. A single equation gets us 6 conversion factors. Okay? How many different equations, chemical equations, are known? A lot. Thousands upon thousands upon thousands, arguably an infinite number of chemical equations are possible. So every time we get a new chemical equation, we get a new conversion system, which is really, really cool. As long as we know how to pull that information out to establish those relationships, we have a lot of power at our fingertips. And that's what I want you to be able to pull from a chemical equation. That's the value and use to it. Okay? So, with that, just like we did with the last video, we've now got a whole bunch of kind of practice now sequencing up. So how many moles of oxygen react with 2.25 moles of nitrogen? Okay, so in this case, what are we solving for? What do I want? Well, what I want are the moles of oxygen. Why do I know it's O2 and not just an O? Does it say atoms of oxygen? No. So we know it's O2. Okay, another tip off, look at the chemical equation. It's showing us as O2. What was the given information? Well, we're technically given 2 pieces of information. We're given the green thing, and we're also given that purple chemical equation. Okay? That purple chemical equation gives us lots of conversion factors. We would have to know which ones that we want to use. Okay? So take a second, pause the video again, see if you can come up with your conversion process. Yeah, that would be the space bar again. Okay, presumably now you're back because you've come up with some process or you've gotten stuck and you don't know where to go. Okay, my argument again for starting this whole thing off would be to pick something that I know has to show up. I know I need moles of O2 to show up in the numerator. Okay, because that's what an equality means. So I would start with the moles of O2. Okay, am I given the moles of O2? Well, I could go up into my green box. That green box says moles of nitrogen. Well, what is the symbol for nitrogen? That would be N2, so that's certainly not O2. The purple does have O2 in it, okay, that purple box. The moles, yep, chemical equations give me moles or molecules or atoms, depending on what I'm looking for. Since I'm at moles, I could do this. The number associated with that, assuming this was a balanced equation, would be 1. So I could even put in a number there. Okay, but because it's from the chemical equation, it's not that I have 1 mole of O2. It's that I know 1 mole of O2 can be related to nitrogen or NO2. So I need something in the denominator here. Okay, I have to specify either N2 or NO. So if we wrote moles of NO, this is a valid conversion. Okay? And before you start saying, oh, I didn't write that, that's okay. Don't stress about that. For this conversion to work, what would then need to happen is I would need to introduce moles of NO, right? Well, am I given just the moles of NO? If we look back to the question, I'm not given just the moles of NO, I'm given the moles of N2. I do see NO show up in a chemical equation, and it is 2. But again, because it's in the chemical equation, it's related to something else. Okay, I can't just pull that 2 out. That 2 is intrinsically tied to everything else within that. So if I'm going to write moles of NO there, I would also have to write moles of something else underneath. Before we start going down that path, what I'm doing is undoing the work that I had just written in. If you find that you are undoing something that you've done, you probably shouldn't have done it to begin with. So writing the moles of NO was a bad idea. What do I want to write instead? Well, if moles of NO was a bad idea, then I'm not going to pick NO. O2 was already written, so that's off the table. That means I need to be using N2. Well, how many moles of N2 does it say I should use? According to the chemical equation, there's nothing written in front, so it's a 1. I know the moles of N2 would need to cancel for my equation to work out. Am I given just the moles of N2? Yes, sure enough I am. I'm given 2.25 moles of N2. Now I can establish that all I have to do is the math now, multiply 2.25 times 1, divide by 1, and I get 2.25 moles of O2. Okay? This was a trivial solve. They were all 1s, so it didn't really matter. Okay? But this is also a single conversion. What happens if you have to do 5 or 6? Okay? It becomes difficult to track if you're just jamming numbers in. If you write down your units appropriately, both the measurement and the substance, you can track where you are at within your calculation, and you can ensure that you don't miss things. Okay? What would go in the denominator under the green? Just a 1, because again, that was a single piece of given information. I don't want to alter it. Okay? Your textbook, because this was a textbook slide, gone through, shows the exact same work. But now it shows it all as one piece. So again, the piece, the final solve, isn't useful for you. It is what is the process that you're using to place that information in. Okay? So make sure you're considering that when you go through to establish these solves. So here's an equation again. We could go through and try and set up some questions. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Okay, there's a lot of text. I want moles of CO2, okay, and I'm given 1 mole of sodium hydrogen carbonate. I'm also given the chemical equation. So what information do I choose to start with? Okay, and again, it's personal choice. I'm going to choose to start with the purple chemical equation because I know I need moles of CO2. What do I want to relate those moles of CO2 to? Because the chemical equation is not an individual piece. It's a relationship. That relationship has to show up as a fraction or a conversion factor. Okay? It can't show up just as a single piece of information because that entire box is not a single piece. It has, in this case, 4 pieces. Okay, what do I want to relate it to? Well, I think relating it to moles of sodium hydrogen carbonate is going to make sense because the given piece of information is just sodium hydrogen carbonate. So now that I've established which 2 things I want to relate, now I can bring in the conversion or the numbers. The number in front of CO2 is 1. The number in front of sodium hydrogen carbonate is 2. Okay. I know moles of sodium hydrogen carbonate must disappear. So I'm going to place that in the numerator so that that unit can cancel. The number associated with it from my question was 1. And I would now see that I get 0.5 moles of CO2. Okay, neat. I've got to solve. But let's hold up here. Okay, remember how we did that bike example not too long ago? And we said we could either get 1.5 bikes or 2 bikes. And we said that our answer ends up being only 1 bike because we can't have half a bike and we couldn't make the 2 bike. Well, can I have half a mole of CO2? Am I allowed to do that? I couldn't have half of a bike. Can I have half of a CO2? We might need to listen to that phrasing once again. I can't, or can I have half of a mole of CO2? Can I have a molecule of CO2? Those are 2 different questions. One is a molecule, one is a mole. I cannot have, not have half a molecule of CO2 because the smallest indivisible piece for us is a single molecule. So a half a molecule of CO2 doesn't make sense. But a half a mole? Well, what is a mole? A mole was 6.022 times 10 to the 23rd molecules. Can I have half of, let's pick a number that's easier, 1,000 molecules? Yeah. So a half a mole is actually a valid thing. We can work with half a mole. We can't work with half a molecule. So again, this scale up to moles allows us to actually do some interpretations that we wouldn't typically be able to do at a molecule scale. And that's kind of neat. Okay, so we've got a new question here. How many moles of sodium hydrogen carbonate are produced when 1 mole of sodium carbonate, and this is by extension, 1 mole of water and 1 mole of carbon dioxide mix? Okay, so what I want you to go through and do is set up the work to solve that. Okay, that is a trivial one, but again, address the work. The work becomes important in this. Okay, and I'm actually not going to show it. Okay, so the next question. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? So this was similar to that if you only have 2 wheels question, because we're really only saying we're giving you just CO2. We got to be a little bit careful here. We aren't saying you just have 2 moles of CO2. We're saying 2 moles are being consumed in the context of this question. If 2 moles of CO2 are consumed, we had to have enough of the other 2. Okay? So we're actually assuming an infinite amount of sodium carbonate and an infinite amount of H2O, so that we don't have to establish a conversion that you did in the previous question. In this case, we can get away with just 1 conversion. Okay, so what is that 1 conversion? Well, what are we being asked to solve for? I want grams of sodium hydrogen carbonate. Okay, and now what am I given to start with? Okay, so again, we're given a lot of stuff. So I'm going to try and color code and simplify things. We're given 2 moles of CO2. And then we're also given this big honky chemical equation. Okay? So what I'm going to ask you to do is to see what you can come up with on your own here for a second, and we'll see you after you come back from hitting pause. That was the space button or clicking the pause button. Okay, so let's assume you're back. And maybe you were like, well, what the F, Mike? If I go through and look at this, I've got grams and sodium hydrogen carbonate. Well, the only place that sodium hydrogen carbonate shows up is in my chemical equation, but the measurement unit for that isn't grams, it would be moles or molecules. So I don't have in any of this explicitly given information the measurement of grams. Where do I start? Okay. Well, the easiest answer for me to go through and do is to start with the only place that you know. Okay? 2 moles of CO2 is using both a measurement and a substance that you don't want in your answer. So that's probably not a good place to start. The chemical equation does give you your substance. So I'm going to start with that substance and hope that if I work through this, maybe an answer falls out for where I want to go. So what do I want to relate this sodium hydrogen carbonate to? Well, the only other given information I've got, other substance, is CO2. So probably relating the moles of sodium hydrogen carbonate to the moles of CO2 is a good idea. The number values come from my chemical equation, the coefficients from there, and we've got that expression. We could then go through and recognize from that given piece of information, because this came from our chemical equation, in fact, our balanced chemical equation. So we've got that balanced chemical equation conversion in there. And now where do we want to go? Okay, well, I still don't know what's going on with the grams of grams of sodium hydrogen carbonate. So I'm going to just leave that alone for the moment. I do know that I don't want moles of CO2, right? So the moles of CO2 are going to need to cancel with something. So I'm going to place moles of CO2 in the numerator and hope that somewhere moles of CO2 show up in the given. Oh, sure enough. There, in the given information, I know 2 moles of CO2. Okay, what is that being related to? It's not being related to anything. It's 1. Okay, so my moles of CO2 would cancel. Fantastic. That is great. I simplified it. I now have just the substance I want, but I don't have the measurement unit. Okay, so if we think back to the processing I've been asking you to go through and do, what we should now do is continue with that and just see if maybe we can get a clue by writing that information down on where to find this. I know I need grams of sodium hydrogen carbonate. And I know that needs to appear in the numerator because that's where it is in my answer. I also know that moles of sodium hydrogen carbonate needs to appear in the denominator so that that unit can cancel, right? So this conversion factor, I want to exist. Okay? I want the conversion factor that relates mass to moles. And if I have that, I have my answer. Based off of our last video, you should recognize that we do have that. That conversion factor is found on the periodic table. And what I can go through and do is sum up the masses for each of my individual species. And of course, I'm going to run out of room. Oxygen 16 times 3. And I would get that the mass is equal to a whopping 84 grams per mole. I could place that 84 into my calculation, grams per 1 mole. My units all now align and cancel out. All I have to do is enter this into the calculator, and my calculator spits out that I should end with 336 grams of sodium hydrogen carbonate if 2 moles of CO2 were consumed. Ta-da! This is the beauty of our process. As we move through, we're picking things that we've got and just trying to get them to work to fit this system. Okay? If you move through it slowly and address according to the methodology that I asked you to practice in Unit 2, this is now relatively straightforward, and the conversion factors that you need to find kind of fall out naturally from the process. If you've been fighting that process, you now have to be like, well, what conversion factor do I bring in? And you start slamming stuff into it and hoping it works. Sometimes it does, sometimes it doesn't. Okay? In that kind of slam things in, really what you're relying on is that you've done enough practice that you've effectively memorized an algorithm for how to solve. Okay? Not the best method, but it does work. Okay? This kind of question should look familiar to you because it is very similar to the question being shown here, which was on exam 2. Okay? And I usually get people on exam 2 being like, well, this question's entirely fair. There's no way I could answer this. Everything about this follows the process that we've addressed to this point, and even to the point in Unit 2. It allows us to solve. You just have to know how to manipulate those conversion factors. Again, according to the process that I've told you. Okay? What happens in this next unit, though, is that most of those conversion factors you are required to derive and understand where they're coming from. So that question now becomes this. All of those conversion factors that were given to you, you have to be able to pull out of the context of the question. Okay? And that becomes challenging. Okay? So let's go through and address what is some of that context. So first context, oxygen gas reacted with hydrogen gas to produce water. We're being told a chemical equation. We need to know that oxygen and hydrogen are both diatomic elements. We would need to know the formula for water is H2O. We would need to be able to recognize that this equation is unbalanced, and we would balance it by placing coefficient 2's within that. This gives us a conversion factor that allows us to relate oxygen gas to the water produced in our question. Okay? Another conversion factor that we're going to have to pull out of this. Oxygen gas, since we know it is O2, we can go through and determine that it has a mass of 32.0 grams of O2 and 1 mole of O2. How do I know that? Because I know that relationship is found in the periodic table. I also need to be able to pull out the grams of water. I would need to recognize that 18.0 grams of water are found in 1 mole of water, also found by understanding the chemical formula and the periodic table. Okay? How do we put all of that together? How do we know we would need all of that information? Well, let's go ahead and clear everything away, and let's look at the question. What am I being asked to solve for? Grams of water. Okay? As far as given information, the only explicit given information is this grams of oxygen gas, which I could rewrite just because it's a bit wordy there. 9GO2, and there's our given information. Okay? We're also given this reacted with and this hydrogen gas, which should be a tip-off that we're looking at a chemical equation. Okay? O2 plus H2 to produce H2O. The chemical equation gives us conversion factors if it is a balanced chemical equation. So we would then need to acknowledge that we need, and actually it gives us conversion factors. Let's just address that for the moment. Okay? Do I need a conversion factor? Well, I'm given O2 as a substance, and I want to end with H2O. So am I converting a substance? Yes? Then yes, I need a balanced chemical equation. So I'm going to go through my process for balancing it. I can now go through and say, well, what do I want to do? Well, I know I need H2O as a substance. I know I'm given O2 to start. Where do I find the relationship between those substances? That comes solely from the balanced chemical equation. Okay, and the unit associated with that would be moles. I can pull coefficients from my balanced chemical equation, and I know I have 2 and 1. Moles of O2 is something I certainly don't want in my solve, so I could place moles of O2 in the numerator so that it cancels. But I'm not given the moles of O2. I'm given grams of O2. So if I'm paying attention, I don't want grams of O2. I could go through and say, well, if I can figure out this conversion factor, I could then drop the grams of O2 into my solve, and that would now cancel. Where do I find the conversion factor that relates mass and moles? That would be the periodic table. A single oxygen weighs 16. There are 2 oxygens in O2. My mass is 32 grams and 1 mole. If we're now tracking my units, because we've now got the ability to do some canceling, the moles of O2 cancel, the grams of O2 cancel, I'm getting dang close to my final answer, except if I compare, I've got moles in grams. So I need another substance conversion. In that substance conversion, grams needs to appear in the numerator, moles needs to appear in the denominator, and it needs to be for the substance of H2O. How do I know it needs to be for the substance of H2O? Well, because I wrote proper units, I can see that those substances need to be there. Well, where do I find the relationship again between mass and moles? That again goes to the periodic table with hydrogen with a mass of 1, 2 of them, oxygen with a mass of 16. This gets me to a mass of 18, and I get 18 grams of O2 is 1 mole, grams of H2O is 1 mole of H2O. The moles of H2O do a long distance cancel, and if I now track all of my units through this given process, I now have the ability to go through and solve. What does that solve come out to be? A whopping 10.125 grams of H2O. We should consider sig figs. I know I've actually been avoiding that question. We get 3 sig figs because we were given 9 grams to start, which is 3 sig figs. So 10.1, the 2 and the 5 are going to be insignificant, and our answer becomes 10.1 grams of H2O. Because you might have a question and say, well, aren't there sig figs in our individual conversion factors? Okay. Say from our balanced chemical equation, the balanced chemical equation has infinite sig figs. Okay, those are defined units for those. The molar mass conversions that are coming from your periodic table don't have infinite sig figs, and those could control your answer. Okay, because those are things that you're looking up to calculate. What you should go through and do is ensure that the number of sig figs in those conversions is larger than the number of given sig figs. Okay, in this case, I didn't really do that. I did some rounding, but that rounding actually doesn't have an effect here because of where the molar mass of oxygen and hydrogen are. Okay, and we now have our entire process with all the nitpicky details and pieces associated with it. Okay, so all we're really doing in Chapter 9 is introducing that new conversion factor that we've got in purple, which is our chemical equation. How do we relate substances to each other? Okay, when we relate substances, it has to be the same measurement, and that measurement unit is a counting unit, either moles, molecules, atoms. Okay, it is not a measurement as in grams, milliliters, liters, any of that kind of stuff. Okay, so we're going to end this with just a bunch of kind of summary slides. Ultimately, what we're trying to push to is dimensional analysis. Okay, why? If you have to take more chemistry, dimensional analysis is what you're going to do. Every chemistry instructor is going to expect you to be able to do dimensional analysis. Okay, you don't need dimensional analysis, again, because you don't have chemistry. You're probably wrong. Okay, what you'll end up doing is having an algorithm given to you to force your conversions. Okay, so that you don't have to think about it. If you're planning on going into nursing, one of the tests in nursing is to do a bunch of conversions, because conversions matter when it comes to how much drugs you should be giving somebody, and if you overdose them and they die, that could be your liability. So they ensure that you know how to do conversions. Okay, so you'll see it show up again. How important is it then? If you fail that test, you're out of the nursing program. Okay, so if it took you 5 years to get into the nursing program and you fail the test, you can still become a nurse. You just have to wait another 5 years of application cycles to get back in so that you can retake that test. Okay, different institutions have different requirements behind that test, but as far as I know, all institutions require that conversion analysis because it is of critical importance to giving drugs to patients. Okay, the beauty of dimensional analysis beyond nursing, science or any of those is that this process works all the time, every time, for everything. There's not a single thing that it doesn't do well for. Okay? So if we go through and look at our general process again, what we've got here is this desired. This is our want. This is our have. When we go through to convert, we want the have in the denominator. We want the want in the numerator. Those wants and haves may change. We may have multiple iterations, but those are allowing us to do those conversions. So identify what you want, identify what you have, want over have, every single time. It'll work. Okay, we got the equalities for that. Okay, y given in that format. That equality allows us to convert a to b or convert b to a. Okay, where are those conversions? Where did we get them from? If they're measurement conversions, those measurement conversions are ultimately all chapter 2 stuff. You'll find it in the textbook, on your exam, or in your brain. Okay. In our chemistry conversions, we got a lot of conversions listed out down here. Going atoms to AMUs can come from the periodic table. AMUs to grams ends up being a weird, goofy conversion if you wanted to use that. You can do periodic table, molecular mass, grams to moles come from a balanced chemical equation. Okay, so all of those conversion factors allow us to manipulate and convert between them. If you don't know where you're going, you're just throwing conversions at it and hoping it works. This is why you use dimensional analysis. It always keeps that end goal in mind so that you know which things that you should be attempting to do. Another way to look at our conversion factors is just where to find them. They're all kind of listed out here. Again, it's just another format for how you could potentially see and go about finding these things. Okay, so with that, there are tons of practice questions for dealing with moles and mass in the mole chapter, chapter 8, and then tons of conversions dealing with substance conversions or chemical equations in chapter 9. You should be going through and looking at those because we're going to make them more complicated by looking at different ways that we can measure these things. At this point, all I'm asking you to do is say we're measuring by mass. How can we get these into units that we can manipulate through a chemical equation? In chapter 8 and 9, they reference volumes. I don't want you looking at volumes yet. Okay? That is going to happen very, very fast here. But I want you to be careful when addressing volume measurements because there's different ways we can deal with those. Okay? And that's going to be the next probably 2 lecture videos. One on volumes from solutions and one on volumes from gases. With that, I'm going to go ahead and stop and give you time to hopefully absorb and practice this.